Welcome back to The Explainer. Today we are breaking down one of the absolute cornerstones of digital privacy, something called symmetric cryptography. It's the concept that really protects so much of your digital life.
All right, so to wrap our heads around this, let's start with a really simple analogy. Imagine you have a secret message and you need to send it to a friend in a locked box.
The process is pretty straightforward, right? You put the message inside, you lock it up with a specific key, you mail the box, and then your friend uses the exact same key, an identical copy, to open it up and read the message. Seems simple enough, but there's a problem.
And that right there is the million-dollar question. It's the single biggest challenge in this whole thing. I mean, think about it. How did your friend get that key? If you mailed it, someone could have copied it. And what if they live on the other side of the world? This is a problem that cybersecurity experts have been wrestling with for decades.
So let's see how this whole locked box idea actually works in the digital world. Because this simple concept, well, it's the secret weapon that protects enormous amounts of our data every single day.
The digital version of this is called symmetric cryptography. You might also hear people call it private key cryptography, and that name really nails it. The security of the entire system depends on keeping that one single key completely private between you and the person you're communicating with.
So obviously, we're not talking about a metal key here. The key is just a piece of digital information, a string of data that an algorithm uses to basically scramble your message into total gibberish. That's the encryption part. Then, that same exact key is used to unscramble the gibberish back into your original message.
And what's really fascinating is that even within this one-key system, there are different ways to do the scrambling. You've got what are called stream ciphers, which encrypt data bit by bit, kind of like a flowing stream. And then you have block ciphers, which chop up the data into fixed-size chunks and encrypt each block. A really common example of a block cipher, one you've probably heard of, is AES-256.
So you might be wondering, if it has this huge key sharing problem, why is this method used so much? Well, it has one massive advantage, but it definitely comes with that one big catch we've been talking about. And this chart says it all. The main benefit here is speed. Symmetric encryption is just incredibly fast and efficient, way faster than other methods. And because they're so fast, they're basically the workhorses of the encryption world. They are perfect for the heavy lifting. We're talking about protecting huge things like your entire hard drive, big file transfers, or even streaming video, all without slowing everything down to a crawl. But here is that catch, and it is a big one. This quote really hits the nail on the head. The security of all that data, everything, is completely dependent on keeping that one key a secret. If that key gets out, well, it's game over. So you see, we are right back where we started with our locked box. How do you get the key to your friends safely? In the world of cryptography, this is called the key exchange problem, and it's the fundamental weakness of symmetric encryption when you use it all by itself. Thankfully, modern systems are way too clever to use it alone. They use this really elegant solution that combines symmetric cryptography with another method to solve this exact problem. This other method is called asymmetric cryptography, or as you might hear it, public key cryptography. And as the name suggests, it works in a totally different way. Instead of one shared key, it uses a pair of keys. This table gives us a great side-by-side comparison. You've got symmetric with its one key, which is all about speed and encrypting lots of data. And then you have asymmetric with its two keys. It's slower, yeah, but it provides a really secure way to handle the key exchange in the first place. The way this works is just brilliant. Imagine the public key is like an open padlock that you can send to anybody. They can use that padlock to lock a box. But, and here's the magic, only you have the private key that can open it. So anyone in the world can lock something for you, but you're the only one who can unlock it. Okay, so how do these two systems actually work together? This is where modern cybersecurity gets really, really elegant. It combines the strengths of both to create something that's both fast and secure.
See, we don't actually have to choose between the speed of symmetric and the security of asymmetric. We can use a hybrid approach that takes the best parts from both systems.
Here's how it plays out in practice. First, a brand new, temporary symmetric key is created just for this one message. Second, you take that tiny symmetric key and encrypt it using the recipient's public key, that open padlock. Third, you send both things together, the big, symmetrically encrypted message and that tiny, asymmetrically encrypted key. And finally, the recipient uses their private key to unlock the symmetric key, and then they use that fast key to unlock the actual message. So the takeaway here is that we're using the slow, super secure method for the tiny but vital task of sharing the key, and we're using the fast, efficient method for all the heavy lifting of encrypting the actual data. It really is the best of both worlds. Which leaves us with a final thought to chew on. If the math and the technology behind our encryption are this strong, where do the attackers focus their efforts? Well, when you can't break the lock, you start looking for a way to get the key from the person who's holding it.